Okay. Great. Thanks, everyone, to join today. So this event, it will be, I think it's the first time that we do such an event to celebrate the independent mapping project that the year 2 years, so that the students, the undergraduate students do at the end, they start this project at the end of their year two, and do most of the work during their year 3. So it's a really big outcome in front of a geology undergraduate student. So today what we will do is that we have with us Laurent Jolivet, who is a professor at Sorbonne University. Laurent was my PhD supervisor. It's mostly why I invited him, mostly for that you are known, Laurent, in I think in the geologic community. Of course, it's a joke. So Laurent will give a talk. I think it's the talk that you gave at the EGU when you received the Holmes Medal. Yeah, so really nice thing. And then the idea was to ask the students who get the best mark to their independent mapping project to present their work. So it was Athanasios Klidaras, but Tinos, unfortunately, was very feeling unwell during the night, and it's still the case today. So what I'll do is that I'll try to present what Tinos has done. I would have asked Philippa Masson to do that because she was the coordinator of the module and knows a lot more than me about Tianshan geology, probably. But of course, Philippa is not here, so I'll do my best to present Tinos' work just after that. But before, I'd like Mark Sutton, as you're here, to say few words mostly to the students.
Yeah, thanks, Valentin. Well, first of all, so thanks for organising this, and thank you, Laurent, for coming along, and to all the students are here as well. So this is an idea actually that came from student suggestions. In fact, I think it was from an NSS survey comment that it would be great to see mapping projects celebrated more, and we absolutely leapt on that and agreed when we saw that suggestion, because mapping projects are such a vitally important step in becoming a geologist. I mean, my experience when I was an undergraduate was that the mapping project was the point where I went from some stumbling inept youth who occasionally hit a rock with a hammer but didn't really know what I was looking at and felt a bit confused, to the point where I came away confident and able to deal with unexpected geology and to just understand geology at a much deeper level. I think mapping projects are a critically important part of education. It's something that we've always valued, we've always protected, and we've always ensured as part of our geology degree schemes. And even during weird remote COVID time, we provided in the best possible way we can different ways to do what are essentially mapping projects, generating the same skills as we did in the real world, because it's so important. This is where you learn to be a geologist. And from what I've only marked 2 or 3 of the mapping projects this year. I've marked plenty over the years, but from what I've seen, all of the same skills have come across. And I've been really impressed with how well people have adapted to the weird COVID world, and how people have produced what are basically mapping projects done to a really high quality. And I think people have got the same things out of it. So I just want to say again that this is really important. Mapping projects are the core bit of fundamental geological degree. An MSci project, for those of you who are staying on next year, takes you further and more into the world of research, perhaps, rather than fundamental geological skills and ability to interpret real geology that's out there, although there is some overlap between the two. But I'm really pleased to see that people are here and are here to celebrate the wonder that is mapping projects, because I think they are absolutely at the core of our education. Okay, and that's all I wanted to say.
Great, thank you, Mark. Thank you very much. Yeah, really agree with everything that Mark has said. Of course, today we will present, after Laurent's talk, the works of Tinos. But most of the students did worked on the same topic. Not all of them. They had the choice between 2 different mapping projects. But I think sort of 80 to 90% did the same thing. And you all did a really nice work and a really good job. and even more difficult this year because it was a remote project, and you were the first cohort to do that, to work on that. So it was not possible to question older year students on what they did because you were the first. So it's even more impressive what you've been able to do this year. Okay, great. So I'm not sure that Mark Sefton is there. That's completely right. So probably, Laurent, if you want to share your screen and start your presentation, your seminar.
Do you see my screen, Valentin?
Yes, and
Okay.
Yeah, it's working.
Yes, perfect.
Okay,
Thank
great.
you, Laurent.
Well, thank you very much, Valentin, for inviting me to this event, and especially as you mentioned that it's the first of its sort. I was very happy to hear also that mapping is considered a very important part of the training of geologists, which is quite obvious, but not always accepted in all universities. So it's good to hear that it's still alive in your place. So I'd like to. It's true that this talk is the talk I presented in not in Vienna, but through Zoom a few weeks ago. So it's what I'm doing now and what I've been doing during the last few years with a lot of colleagues. But I would mention Claudio Faccenna with. In Rome, and will soon be in Berlin, in Potsdam actually, and many others, and you will see also the input of many PhD students, including Valentin, of course, because he worked in the Cyclades with us. So what I would like to show is how we work, we field geologists, on this difficult question of orogenesis or crustal deformation in general and mantle convection. Lithospheric deformation and mantle convection. What is the contribution of a field geologist on this first order question? Okay, you can imagine that mantle convection would be addressed by seismologists or geodynamic modelers and so on, which is of course true. But we field geologists, we have a lot to say on this question, because the only record of anything occurring in the Earth is what has been recorded in the geology, if you want to work on the long term. So let's see how we work. So I'll go around a number of approaches at various scales and show you a bit of few results that we have acquired during the last years and some conceptual models or numerical models. So first of all, from field observation to conceptual models, and I will use the example of the Aegean region, which Valentin knows very well. So you see in the upper left here a tectonic map of the Aegean region and Turkey, and you see, do you see my mouse here? I guess we do. So you have here to the south of Crete the Hellenic subduction zone with a huge accretionary wedge here called the Mediterranean Ridge, and to the north of it we have the Aegean Sea, and the Aegean Sea sits between continental Greece here and the Peloponnese and Turkey on the eastern side. And you have to consider that in the Eocene there was a continuous mountain belt here called the Hellenides here and the Taurides on the eastern side. And this mountain belt has collapsed starting sometime during the latest Eocene. And since that time, the mountain belt has been dismantled, and what you have now, because of slab retreat, is this backout basin that we have here. So if I if I show this along this line here, a cross section with two different interpretations, but let's stick on just one, of the Hellenides, where they are not too much affected by extension. It's a typical, I will not insist on this section, but it's a typical alpine type mountain belt with a suture zone with ophiolite that you see here in green or in the internal zones here. And then continental crust that has been shortened with a number of tectonic slices and with a thrust front migration toward the southwest here. So it looks like the Alps, if I may say so, and even the tectonic timing is quite similar to the Alps. If we now look to the same region, but on a north-south section, going from northern Greece all the way to the subduction front here, north of Libya. So we have migration here, but it's the migration of the magmatic arc from 35 million years to the present. The magmatic arc is here in Santorini, for instance. And this magmatic arc migration is related to the retreat of the slab, the African slab subducting beneath the Aegean Sea here. And the Aegean Sea, the crust has been thinned during this and due to this slab retreat. So we'll see a few examples of structures, spectacular structure that we see here in the Cyclades with spectacular detachment and so on. So let's focus on first on the present day deformation. You see here the focal mechanisms of earthquakes, and you see in red the compressional focal mechanisms. You see them close to the subduction zone here, of course. You see in green strike-slip focal mechanisms, especially along this huge fault here. That is the North Anatolian fault that accommodates the westward motion of Anatolia here, or along the East Anatolian fault here. And in blue, you see lots of extensional earthquakes. And these extensional earthquakes, they are more numerous in the western part of Turkey here, around the Menderes Massif, or in continental Greece, or here in the Gulf of Corinth, which is a very active rift here. You see that the center of the Aegean Sea is quiet actually in terms of seismicity. This is partly a false impression because the largest extensional earthquakes ever recorded in Greece is this one here that occurred near Amorgos in 1954. So it's quiet, but it's this place here that we'll be talking about that has been very active during the Oligocene and the Miocene, and which gives these so spectacular structure that I will show you. So this active extension is actually the present day continuation of a long process that started some 30 or 35 million years ago. So if we now focus more on the Aegean Sea itself, there's no point in describing all these structures here. You have the different nappes here. You have several exhumed metamorphic units that we will come back to later on. What's quite important is these red arrows, and you see these arrows, they point either to the north or northeast, or toward the south or southwest. So they represent the for each of these islands. For instance, here Tinos. We'll go to Tinos in a minute. This is Andros, or here Tinos. Each of these arrows represent the sense of shear along the main extensional structure that is here, the so-called NCDS, North Cycladic Detachment System here. And you see that the pattern you see is quite simple. Okay, if you accept the arrows in the Peloponnese that has rotated quite a bit some 15 million years ago, you see it's always north-south here. And then reaching this latitude here, it turns toward the northeast. But Otherwise, the geometry of the pattern of the direction of extension is very simple in that area. So we have one major event of extension that lasts for, say, 20 million years. That results in the formation of metamorphic core complexes, as we will see, and it is accommodated by large detachment. So these detachments, there are the NCDS, as I mentioned, the North Cycladic Detachment System, the WCDS, which is the West Cycladic Detachment System. Should mention also others like the Naxos-Pyros fault system here, or the South Cycladic Detachment here. So let's have a look first to this part of the Aegean Sea in the east, and we'll have a look to what's going on at present. So you might remember that in 2020, in October, there was a rather significant earthquakes that rocked the eastern part of the Aegean region with a tsunami that was observed on the western coast of Turkey. And this earthquake, with a magnitude of 6.9, which is quite big for an extensional earthquake, it was located here. You see all the aftershocks here and the magnitude and the focal mechanisms of some of these aftershocks. And this earthquake, it's related to north-south extension, as shown by the focal mechanism here. And the main fault is a north dipping fault here that you see here on the cross section. The main shock is along this fault plane at say 12 kilometers deep here. So it's not the first of the large earthquakes recorded in that area. You had several ones to the south here in the 20th century. So you see active extension here is accommodated by north dipping faults here. And this is a picture of one of these recent faults on the northern shore of Samos Island here. You see it's an almost pure normal fault here. If we go now to the western part of the Aegean domain in the Gulf of Corinth, we have an even more spectacular example of rifting with north-dipping normal fault and rather large earthquakes here. So you see a tectonic map of the Gulf of Corinth here. You see offshore the thickness of the thin rift deposit in blue here. You see that the thickness goes to above 2,500 meters here. You see that the main depot centers is offset toward the southern shore of the rift. It's not in the middle. And you see also that the main thin rift deposit have been exhumed on the southern margin. Here it's all the yellow and pinkish and brown colors that you have here. And they've been exhumed by these major normal faults that are shown in red here. And they are all north dipping. You also see that the main earthquakes that show north-south extension, their epicenters are located on the northern shore of the rift here. So we have a really asymmetrical structure here at crustal scale. We'll come back to this region afterward, but you see that the normal fault and the thin rift deposit that you see here, they are limited to the south by this violet color fault here, which has obviously a very low angle. If you look at its geometry on the map here, it's a very low angle detachment, and below this detachment we have metamorphic rocks that I will show you later on. So one of these major faults, this fault here, is like this. It's called the Eliki fault, the name of a small village nearby. And you see that it is also a pure normal fault, very spectacular. And this fault moved last time in the 50s. I think it was in 1950. So if we look first at what is going on the eastern part of the rift, well, I didn't say that the extension is very fast. It's 1.5 centimeter per year, which is very fast for an intracontinental rift. It's 3 times as fast as the Balkai rift or the East African rift. So you see here that the main fault here is steep, steeply dipping. It dips toward the north here. It bounds to the south here in the hanging wall, a fan of sediments with the it's a half graben, very asymmetrical here. And the footwall here is characterized by uplifted terraces that you see here, quaternary terraces, marine terraces. And you see the shape along this cross-section of these terraces here. And they show a very nice flexure here, an elastic flexure that has been, its formation has been dated rather precisely. So this is the work of Fernandez Blanco and others, but it started with the work of Rolando Armijo in 1996. And they've done a very nice work in the eastern part of the rift here. The deposits offshore, they are now well characterized here with very nice seismic profiles shot a few years ago, some 10 years ago now. You can find all these profiles in this paper by Brian Taylor and others. See, if we now move to the western part of the rift here, the geometry of faulting is a bit different. So you see here another map of the same area. So you have the big faults here. The Eliki fault that we saw is here. And you see here all these thin rift deposits in yellow. And you see again this low angle normal fault here that bounds the in its hanging wall here the basement here is in green or in blue, and the thin rift deposits here. And you see that the footwall is made actually of several units, and the deepest of this unit is shown in brown here. And this unit is a metamorphic unit that has seen some high pressure, low temperature metamorphism, say blue schist metamorphism, sometimes in the Oligocene all the way to the earliest Miocene. So if we focus on the detachments itself, just above the detachment here, we have this sort of structure here in the blue material here, which is called the Gavrovo-Tripolitsa nap. It's Triassic limestones here. And you see that these limestone, they are affected by low angle normal faults here. It's actually a huge zone of cataclasites, and you see the layers here are disrupted and offset by these low angle normal faults here. And this is just above the contact with the metamorphic rocks and what comes right above here. So I will not enter into the details of this structure, but if we look now at a synthetic cross-section through the Gulf here, the rift and its margins, it comes like this with this detachment that we have just seen here. And then we have a series of tilted blocks here. And the tilting and all the information we have on the detachment itself shows that the detachment is a top north structure, and this detachment is cut to the north, toward the north, by the Elike fault here, then the Aegean fault, which is one of the active faults nowadays, and we have then the offshore deposits here. And the blue dots and the red dots here are the present-day earthquakes. Actually, they are micro-earthquakes. Some of them are very small. Nobody feels them. And from time to time, you have a bigger one. And you see that these earthquakes, they are somehow lined along a plane that is dipping by some 12, 15 degrees toward the north here. And these, I didn't put the Foucault mechanisms of the earthquakes on this section, but the Foucault mechanism of these very small earthquakes here indicate that there is a top north displacement along what could be here a detachment, or a detachment will become a future, a detachment in the future. So you see that the deformation in this region is a mixture of low angle structures, some old ones, not so old actually, they are probably not older than 3 or 4 million years, steeper normal faults, and low angle structures here along which is approximately the brittle ductile transition. And this active extension, as I said earlier, is the present-day continuation of a long process that we will see just after it. So let's focus on the exhumed deep extensional deformation in the center of the Aegean Sea in the Cyclades archipelago. Okay. So we'll focus on this region here. This is a zoom of the Cyclades here, and on the left, in the east, the Menderes Massif here. So we have the main detachment that I mentioned before, the North Cycladic detachment system, the West Cycladic detachment system, or the South Cycladic detachment here. And these detachments, they have exhumed metamorphic core complexes. So some of them are very classical MCCs, like these ones here. They are what can be called the hot MCCs, shown in orange color here. We find them in Mykonos here, and the islands of Renia and Delos here in Ikaria, and also in Naxos and Paros or Antiparos here. And we also have some cold MCCs that are shown in blue here, in Andros, Tinos, or here, Kea, etc. So these cold MCCs, they have preserved, they have escaped this episode of high temperature metamorphism here, and they preserved the earlier high pressure and low temperature metamorphism here that dates back to the Eocene, and that are of course reworked by some green schist deformation during the extension. But this is why glaucophane was first described in this small island here. It's called Cyros, where Valentin has worked during his PhD. I wouldn't say that the whole island is blue, but there is a lot of blue in Cyros, as you will see later on. Okay, so if I focus first on this part here, Mykonos, Tinos, Andros. This is a 3D view of that area. You see Andros, Tinos here, and Mykonos. And we'll not enter into the details, but you see that we have a series of detachment here, the Tinos detachment here, the Livada detachment, and the Mykonos detachment that you have here. And these detachments, they reworked this unit that we call the Cycladic blue schist unit, as we'll see. And they also deform some intrusions, like in here, Miocene intrusion, like in Tinos here, or here in Mykonos here. So we'll see some images of these detachment. Here I just put a sort of synthetic evolution of this region in cross-section from the late Eocene here all the way to the Pliocene. And you see the progressive formation of these low-angle normal faults here and the exhumation of metamorphic core complexes. First, these core complexes are preserved, the blue schist paragenesis, and then everything is reworked by high temperature metamorphism and deformation here. Okay, so let's have a look to Tinos here, which is one of the nicest islands here. So this is a drone view of one of the very small island that is very next to the main island. And this is the detachment in orange here, the North Cycladic detachment system. So on top of it, you have what is called the Upper Cycladic unit, where no trace of high pressure metamorphism has ever been found here. And below that, you have the Cycladic blue schist, which has seen the Eclogite facies metamorphism. So here, down here, you had at some stage 22 kilobars. So burial of some, let's say, 70 kilometers or something. And this Upper Cycladic unit has never been below more than a few kilometers. So you have along this structure here a considerable amount of extension of displacement here. We quantified it to something around between 70 and 100 kilometers. So it's a huge structure here. So if we focus a little bit more on this structure, you see along it a series of low-angle normal faults here within here it's a serpentinite of the Upper Cycladic unit, and you see all sorts of kinematic indicators like shear bands or asymmetric folds and so on. They are very characteristic of top to the northeast sense of shear. Another very classical example is Naxos in the center of the archipelago here. So Naxos is actually Naxos and Paros here. It's characterized by a huge dome, high temperature dome here, with a core of Migmatite here. This dome is intruded by a granite here, granodiorite here, in the middle Miocene as well. And on top of that, you have a very well characterized detachment here that is north dipping here, still this is the upper cycladic unit with some sediments here. And you see that the direction of stretching all over the islands here is north-south, and the sense of shear is up to the north. Some images, field images. You see here the upper photo shows you the core of the dome, that's the Migmatite core here in the middle. And you see the mountains on the east and west that are the marbles famous in the world of archaeology. The marbles that make the sort of the mantle of this dome. Again, here the Migmatites here and the marbles, and here that's the detachment in the eastern side of the island. Very low angle detachment and some Miocene sediments and then some Pliocene sediments. If we focus on the granodiorite I showed you, that's the granodiorite here in this pinkish color. And you see the direction of stretching here in it, and the sense of shear is really very consistently top to the north here. And it's very intensely deformed here. You see the enclaves here, mafic enclaves in the granodiorite. So you see stretched along the north-south direction. You see that the matrix of the granite is also strongly stretched here. So we played a game here, which was to identify, to build a sort of strain scale from poorly deformed rocks all the way to very strongly deformed rocks, and even here cataclasites and pseudotachelites here, so from ductile to brittle. And we put a color on each of these grades here. And then we mapped these grades in the field, and you see here the outcome. So you see this gradient of deformation from the blue here all the way to the violet here toward the detachment here. So that's a work we have done on several islands, actually all the islands where there are significant intrusions. So that's Tinos here, that's Mykonos, Naxos, we've just seen it, Ikaria in the east, Serifos in the south here. And so that's the map of the islands. And you see here the strain gradient here in Naxos, here in Ikaria, in Mykonos, in Serifos. So this map here was done by Valentin and during his master internship. And this is the sort of section, the typical section we have derived from these studies, the relation between the metamorphic dome here with the Migmatites and the intrusive body here, which was in place during the displacement along the detachments. We have a series of detachments, 1, 2, 3, progressively intruded by the plutons here. And the end of the story is the formation of a series of dike swarm filled with barite and iron minerals that have been exploited in Mykonos, for instance, or in Serifos. Okay, that's the how it works. So you see, it's really asymmetrical at the scale of the crust here, which is very important for what we'll say afterward. Let's have a look to Mykonos now. So just north of Naxos. So Mykonos is a rather simple island. Most of the island is made of these yellow and orange colors here, which is the intrusion, mostly mounds of granite here. And then to the west, this intrusion roots into a Migmatitic dome that is in the west here. So in the western part of Mykonos, the island of Delos and the island of Renia here. And on top of this, we have a detachment here with the upper cycladic unit, this greenish unit, or this deep green, red unit here. And you see the shape of the detachment here contorted, showing that this is very low angle. And if we draw a section like this, this is approximately what we get with the Pluton here shown in yellow, rooting within the metamorphic dome here, the migmatitic dome. And on top of this, we have the detachment here. And these are the sediments, supra-detachment sediments. So we'll have a look to this area here, which is quite spectacular in the field. You see here with two different lights, it's not so easy to take a picture of that. It's not always well oriented. The lower part of the photos here is the highly sheared granite, and the detachment is here, low angle, and on top of the detachment you have tilted sediments here, late Miocene sediments, conglomerates and so on. And these sediments, they are cut by steep faults routing into the detachment here. So it's a typical textbook example of a detachment. The granite below that is highly sheared, and you see here an example of these mylonite showing top to the east-northeast sense of shear and some ultra-mylonite layers here and here. Within the metamorphic dome here, the Migmatite, we have spectacular structures. That's in the granite here. You see the extension during the cooling of the granite and its extension and its emplacement here, with the stretching of those feldspar here. You see a late dike that gives you the same direction of extension, stretching. You see some enclaves within the granite, and we see a continuum of deformation from the deformation of the host rock here and that of the granite, and you see the very spectacular stretching here. So the history is quite simple, actually. The Pluton is shown in yellow, the detachment in red, and the sediments, thin rift sediments here in the sort of orange color. And what's going on is this, actually. Progressively, you see the intrusion. And remember that picture, because we'll come back to this with a numerical model later on. Okay, so now let's move to what was going on before that, before extension, before the Oligocene. And we'll go to the island of Cyros, where Valentin has worked during his PhD. And to the left, you see Valentin's tectonic map, geological map. He remapped the whole island here. And with three different units, the Posidonia unit, the Crusa unit here, and the Campos unit here. And on top of that, a unit shown in orange here, it's called a Vari unit. It's part of the upper cycladic unit. So this unit has never seen the high pressure. And just below it, in this violet color, you have eclogites. Okay, and the different units here, you have eclogites everywhere, preserved, all these red dots here. Okay, and the difference is in the rate of retrogression in the green schist faces. So this unit is in deep blue here. The eclogite faces and the blue schist faces are very well preserved, and the green unit here, it's almost completely retrogressed in the green schist faces, but you still find here some remains of the eclogite faces. So these rocks, they are really spectacular. So you see this very beautiful picture here of a metagabbro here, with the green pyroxenes here, amphosite replacing the magmatic pyroxene, and this corona of very beautiful blue amphibole here, this glaucophane here. There are some tiny garnets in the matrix. Another very spectacular rock is this metaconglomerate here with mafic pebbles, and these mafic pebbles, they've been transformed into eclogite, and you see that they all have a rim of glaucophane here. Okay? And you see the asymmetry of the shearing here, clearly top to the east. This top to the east sense of shear, you can see it also at a larger scale. And we are along one of the main shear zones here. You see these offset and boudinaged marbles here with very clear top to the east shear bands here. So I will go quickly through the petrology and the dating, just to say that we have good assessment now of the shape of the PT path here, and that all this deformation and metamorphism have been dated by a detailed work on argon-argon with argon-argon on white micas. It is Valentin's work as well, and with in association with a lot of published datings with other methods. And you see here on this section here, from the valley unit here all the way to the deep Posidonia unit, the evolution of ages here. So old ages in this unit which has never seen the high pressure, and then ages around 50 million years here, that's the Eclogite. And then as you go further to the west, that's deep in the section, you see younger and younger ages. And the youngest ages, they are around 18 million years here. That's the age of the main retrogression here. So I will not detail this any longer, but here you have the ages of the Eocene synorogenic exhumation, say within the subduction zone. And here you have the progressive exhumation and downward strain localization during the post-orogenic evolutions. That's the opening formation of the Aegean Sea and the formation of the detachment we've seen before. And then you have smaller strain gradients associated with these age gradients. So if we want to summarize the PT time evolution of this, we can do it like this. Okay, you see different areas here: Crete, Cyros, Tinos, Naxos, with their PT path here, and you see progressively the exhumation with the time moving to the right here, and you see the exhumation of these rocks progressively here. Cyros is in blue, and here Tinos is in green. In blue, deep light blue, it's Crete, and the red is Naxos here. So all I want to say here is that we have a rather precise understanding of the deformation and the metamorphic evolution through time. And using this sort of information, we are able to reconstruct the evolution of this mountain belt and then its disaggregation by extension in the back arc region here. So I will not detail that anymore, but you see the evolution, though it goes very quickly, but it's a very long work to draw this sort of somehow balanced evolving cross-section here. Okay, let's now generalize to the Mediterranean back arc regions. So these back arc regions, you see them here. So you have the Aegean Sea here, you have the Tyrrhenian Sea here, and you have the Liguro-Provençal Basin, the Algerian Basin, and the Alboran Sea here to the west. All these basins, they formed as back arc basins during the retreat of the subducting slab, southward retreat here, southeast, and eastward retreat here for the Tyrrhenian Sea, and southward first and then westward for the Alboran Sea. Okay, and and the ages here are shown by the colors, and you see from the Eocene here all the way to the middle and late Miocene here for the Tyrrhenian Sea. So you see this migration that we've seen in the Aegean Sea. You can see it as well along this transect. So let's have a look to this curved section here, from Provence here all the way to the Apennines. So in Provence, we have at the junction with the Pyrenees here. You see that what's very characteristic here is that we have passive margin. Yeah, you see the Sin Rift deposit, and this passive margin cuts at right angle a mountain belt, which is the Pyrenees. So there is obviously a very significant event here, where this mountain belt has been totally replaced by a passive margin. So the mountain belt is, say, Eocene in age, and the passive margin is started to form in the Oligocene. So there is a short event here in the latest Eocene to the early Oligocene, where this mountain belt was completely destroyed by the rifting. So how did that happen? So to make a long story short, we have worked on seismic profiles, industrial seismic profiles, and these profiles here, they show something very spectacular, which is the exhumation in violet here of the lower crust here by low angle detachments here. And these detachments, they are dipping toward the north here. So that's this profile here through the Gulf of Lion. And you see that all the profiles, they look a little bit alike. The difference with these ones here is that here you have a lot of volcanism, thin rift volcanism here, which makes this light blue layer here. So if we have a look, you cannot read the non-interpreted profile here, but the profile is here in the Gulf of Lion. We have at the toe of the margin, we have what we have called the Gulf of Lion metamorphic core complex here. And it was then covered by thin rift sediments and then the post-rift sediments here. And you have several low-angle detachment. This one here between the lower crust and the mantle, the exhumed mantle here, and other ones between the upper and lower crust. And the evolution is something like this here. You see on this balanced cross section here, you see the progressive exhumation of the lower crust and the upper mantle during the rifting here. So if we now have a look to the Pyrenees themselves, there was recently published a series of profiles across the Pyrenees here, passive seismology seismic profile here. And you see that in the west, A, B, C, there are these three profiles here. We see very well the underthrusting of the Iberian crust underneath the Pyrenees here. And that's typical of the Pyrenees. But you see in the east, on the profile D and E, that this structure is totally lost here. Okay. So there are various interpretations of this. But if you look at perpendicular profile here, and you see that along these profiles, in this region, the moho is coming up until it reaches something like 20 kilometers close to the coastline here. So, and we think that this disappearance of the orogenic structure, the underthrusting here, is due to rifting, and that the root here has been removed by the rifting. So this orogenic structure is totally, that you see in the west, is totally lost in the east. Okay, and so we think this is a consequence of the rifting. So how did that happen? This is our interpretation here along this cross section here, parallel to the belt, along the strike of the belt, and then the Gulf of Lion. It's the lower crust here has been removed from under the upper crust, and the whole system has been thinned by the asthenospheric flow. That's where we reach the convection that we have to talk about now. The asthenospheric flow due to slab retreat. And the interpretation is that this margin here, the formation of this margin, has somehow eroded the Pyrenees from below. Okay, and the lower crust that used to be below the Pyrenees is now here at the toe of the margin, and the exhumed mantle is here. Okay, so a quick look to Corsica here along the same transect. You have here the evolution of the magmatism here, the red stuff here, or the metamorphism here, the blue and green stuff, and you see exactly like in the Aegean. You see this migration of the back arc extension and the frontal shortening here. And you see the migration of the magmatism here. So again, we have this slab retreat that we were talking about. So just a few images. In Corsica here, you have here one major detachment here, which reworks a major thrust of the former alpine mountain belt here, that puts the oceanic units here, the schist illustré, on top of the what would be called in the Alps the Briançonnais, or the Penninic domain here, and this thrust has been reactivated in extension. So if we look at it on from the nearby mountain, you see here the the brillant sommet, if we may call. And here you have the main shear zone here. You see these chevron-like features here. That's the foliation of the main shear zone here. And on top of that, you have a tilted Miocene basin here. So across this shear zone here, we see a very spectacular evolution of the Variscan granite here. You have one of these granodiorite here, and progressively it will be deformed and all the way to ultramyelonites or highly sheared myelonites here. So we have mapped this exactly as we did it with the granites in the Aegean, and you see here the strain intensity from the white here all the way to the red, and you see the strain localization here, also on the cross sections here. And we have dated that, dated the deformation, and we found that we have some old ages. The youngest of them are around 34 million years, that are related to the orogenic history, that's the alpine history. And then we have younger ages that are related to extension and back arc extension. Okay. So it is very similar to what we have seen in the Aegean. Okay. And this goes all the way to 22 million years, is the end of ductile deformation in that area. Okay, briefly, the island of Elba here. So it's another spectacular area where you have low angle detachment. This one, the Zucalle fault, is very spectacular. Or here, the eastern shear zone, limiting the Monte Capanne intrusion here. There is one intrusion here, another one here in this sort of pinkish color, and they are associated with these detachments here. So these granites, they are oriented just like in Naxos or Icaria and so on, and they are associated with, their cooling is associated with the formation of a skarn in the upper unit here, and you see here the synkinematic skarn here with the garnet growing in those veins here, perpendicular to the direction of stretching, and some clear sigmoidal features here. So we came to this sort of image that we've seen already from the Cyclades, very similar in Elba here. And we'll see that more with some numerical modeling afterward. And just to finish up on this section, in the Apennines, we have nowadays, we have extension that is very asymmetric, with top to the east low angle normal fault here, with the associated seismicity. So this is the main low angle normal fault here. It's called the Alto Tiberina fault here, that controls the seismicity in this region. So along this section that we have seen, we have always the same top to the east sense of shear here along low angle shear zones and normal faults, and magmatism in place during the same time. Then to finish up with the field here, the Alboran Sea, you have the same sort of history. I will not enter into the details at all, but we have several detachments, one in red here and one in blue. You see them on the cross section here. Okay, you see also the exhumed mantle rocks here of the Ronda peridotype, and we have several big core complexes, including the Nevado-Filabrate core complex, exhumed during that slab retreat here. So two major detachments here, working mostly during the last period toward the west here. So one good thing to do is to map these units with colors corresponding to the maximum pressure they reached. And you see here that you have more than 18 kilobars in the Sierra Nevada metamorphic core complex here and here. And right on top of that, you have much lower pressure units separated by this main detachment. Okay, here you have still some metamorphic rocks, but on top of that, you have another detachment, and there you have no high pressure, alpine high pressure at all. So crossing these detachments here, you have jumps, very spectacular jumps in pressure here. So One of the detachments is this one, okay, in blue, and you see the kinematics associated with it, and that's before 20 million years. And after 20 million years, we have another detachment in red, and you see that the direction of stretching is perpendicular to it. So it's a bit complex in that area. But if we look at the lower diagram here, you see the evolution after 28 million years of this system with slab retreat and the progressive exhumation of these big core complex. Okay, so with those observations in hand, we can make reconstructions. And Armel Menant, one of our PhD students here, he did very detailed reconstructions of the Aegean. So here you see the Tethys Ocean 100 million years ago. You see all these symbols here, triangles and square, that represent magmatic events, so either volcanoes or plutons here. And you will see the progressive closure of the Tethys Ocean here, and the progressive formation of the Aegean Sea here. Okay, and you see that these the colors of these symbols, they change because the typicity, the type of magmatic rocks change through time because of slab retreat and so on. We can do the same here, the scale of the Mediterranean here, and you see the same evolution here. See the progressive slab retreat and formation of these basins. Okay, so now how do we couple this with slab dynamics and mantle flow underneath? Okay. So the simplest way to do it is to use some seismological information, which is seismic anisotropy. So seismic anisotropy tells you what is interpreted as the direction of flow in the asthenosphere when you use these waves here, the SKS waves. Okay, and if you look at this map, you see that the pattern of the direction of the flow in the asthenosphere here is not random. You see clearly the swing around the Alps here. You see this very consistent direction here in the Aegean here, east-west direction here below the Sierra Nevada here. And if you correlate this with the direction of stretching we've seen in the metamorphic core complexes, you see that everywhere we have back-arc regions, the direction of deformation in the crust, the metamorphic core complexes we have seen before, and in the mantle show the same direction, here in the Aegean, here in the northern Tyrrhenian Sea, and here in the Alboran Sea. Okay, so we have a strong coupling between the asthenosphere moving and the crust. And the idea is that the retreat of the slab here, so let's see here, that's the example of the Aegean, from the earliest Miocene to the present. The retreat of the slab causes a flow in the asthenosphere here, so here toward the south. And this flow in the asthenosphere here controls the deformation in the crust on top of it. That's the basic idea. So if we have a look to the whole Mediterranean, you see the shape of the subducting slab at the present and what it was probably some 23 million years ago. You see the difference. The amount of retreat, you see that the slab has been torn, has detached, and so on. Okay. So now we'll go to modeling. And the idea is to see how these fast displacements are accommodated at depth. Okay. So we have this fast displacement that we have just seen here, shown by these dots here from the Eocene to the present here. Below that, we have slabs, okay, shown by tomographic images. Here you have the Hellenic slab here, you have the Ionian slab here, you have the slab beneath Gibraltar here. And these slabs, they are not continuous, they are torn here, detached, and so on. And we wanted to know the effect, to understand the effect of slab tearing. Okay, and that's what Pietro Sternai, a student in postdoc in Orléans a few years ago, he did some numerical modeling with the code of Taras Geria in the ETH in Zurich. And he studied the effect of slab tearing at depth here on the deformation in the crust here. Okay, so you have slab retreat here, and you see the slab retreat here, and this is the back arc region. So what is got is this. the arrows here are the velocity field in the crust, in the model. And the colors underneath represent the strain rate. And when it is red, it is high strain rate. When it is green, it is low strain rate. Okay, green or blue. Okay. And you can compare it with the direct observations. On the left, on the right here, you have the GPS data here with this rotation that is very well known for Anatolia, the acceleration here. And from this GPS velocity field here, you can calculate the strain rate. That was Pérouse and others did in 2012. And you see clearly the strain rate here with the North Anatolian Fault. You see the high intensely deformed region here, the subduction zone. And you see the extensional region here in Western Anatolia or the Gulf of Corinth. And you can compare directly the velocity field here, and the strain field here and here. And you see that it's very similar. So we think that we have captured here the main mechanism, that the formation of the North Anatolian Fault here is mainly a consequence of slab retreat. Then we did, Armel Menon did a number of other models here involving the magmatism as well. All these colors here are the magmatic events. I will not enter into these details. And you see the migration of magmatism here due to slab retreat. And what is spectacular is this, a cross-section through this model here shows you that the mantle here flows faster than the crust here. Okay, this is shown also on this diagram here, where you have the velocity in red, and you see that the asthenosphere flows faster than the crust because it is dragged by the retreating slab here. And the lower crust here is a shear zone. You have a gradient of velocity, so it's a shear zone. And this shear zone here is top to the north here. The bottom goes to the south, so it's top to the north, just like the major detachment we've seen in the Aegean. So we've tried to model this also to understand how the granites worked in this system. And you see the images I've shown you before here, and you see here the result of one of these numerical models done by Laetitia Lepouriet, just published in Solid Earth. And you see here the progressive formation of a Pluton here, underlined by the white line here, the Pluton and its deformation below the main detachment here. And you see the similarity between this kinematics and what we observed in the field, either in Mykonos or in general in these Plutons. Okay, so you see that there is a profound influence of asymmetrical deformation at the scale of the crust here. And this asymmetrical deformation is mostly due to the asthenosphere. Okay, let's change scale now. At the scale of the continents, Africa, Eurasia, and the Tethys Ocean. So in this region, if we look to reconstructions here, since the Jurassic, we see that this region goes through periods of extension in green, main rifts, and period of compression in yellow here. Okay, and we think that this alternation here and the stress field in general in the lithosphere is mainly controlled by the interactions between the subducting slab, the Tethyan subducting slab here, and the boundary between the upper and lower mantle here. And it's when the subducting slab here attempts to penetrate the lower mantle here that the whole system gets into compression here, this period here. And this is probably for us the cause for the very important large abduction that we had at the end of the Cretaceous on the northern margin of Africa. Then if we go to the eastern part of it, around Arabia, we also think that it's the convecting mantle, and more specifically the hotspots here, the mantle plumes, that controls the separation of Arabia from Africa here from the latest Eocene to the Oligocene and all the way to now. Okay, and that would be the effect of this mantle flowing underneath Africa that would lead to this of fragmentation of continent. And to finish up, I would like to go to another part of the world, which is where I started my geological history, personal one, because I did my PhD in Japan in the field. So that's from the India-Asia collision to the Pacific subduction. So my field area was here in the island of Hokkaido here, northern Japan. And what I found is the existence of a large strike slip shear zone here. And we discovered afterward that it runs through the island of Sakhalin and then goes all the way to eastern Siberia. And this major shear zone here, there is another one here between Korea and Japan, is associated with the opening as a pull-apart basin of the Japan Sea in the back arc region of the Pacific subduction. So the few images from my field area, that was 40 years ago in the Hidaka Mountains here on the summit of these mountains. It was a very pretty area. And this is one of the rivers where I sampled my rocks here. That's the Chiroro River, my favorite river there. The picture is more recent here because we came back there a few years ago. And these are the gabbros that are deformed along this main dextral shear zone here. Very spectacular ones, and this was an old photo, and this is a new picture of these gabbros. So actually, the whole eastern part of Asia, the greenish region here, is characterized by extension mostly during the Oligocene and the Miocene, even though nowadays it's again compressional in Japan. But during the Oligocene and Miocene, all these regions here were in extension. It's a very wide region, while the Tibetan Plateau was growing here on this side. So you have crustal thickening on this side and extension on this side. So the whole of Eastern Asia is totally asymmetrical. And we see, of course, here the influence of subduction, okay, and back arc extension. Okay, so the problem is to understand how this complex system works in 3D. Okay, so I'll skip this well, yes, there are reconstructions that I made earlier on. You see the present day situation with the position of India, for instance, the red line, and the situation some 45 million years ago. And you see that India has indented a lot, and you know that very well, Asia, okay? And here you had this extension here and extension here too. So the system is really fully asymmetric with collision here and back arc extension in the east. If we look at the famous models, especially this one by Toponier and others, the famous extrusion model, which was a very big step forward in the understanding of the deformation of Asia. 1982, you see this model creates the large-scale strike slip fault that we need. It opens basins here, but it doesn't take into account subduction at all. It's almost a 2D model. Okay. Then we did different models here, and again we have these. This is more 3D, and we have some left lateral and dextral basin with some faults with some pull-aparts here. We have Southeast Asia with its extension, but we have no subduction at all. Okay, and this is the interpretation. So we know that extension is associated with slab retreat, and this is not considered in these models. Okay, so the question is, how can we explain the geometry we observe here between this compression here and crustal thickening in the Himalayas and Tibet, and its extension and thinning in Eastern Asia? Okay, and what is driving the interaction between these large-scale strike slip faults related to the collision of India and Asia? Some words are missing here, and back arc extension due to the retreat of the Pacific subduction. And we think that the link between compression in the south and extension in the east is the mantle flowing underneath. So this mantle is flowing. How does it flow? This is the background picture here is the tomography in the lower mantle, just above the core mantle boundary. And you see the hot regions here, the famous LLSVPs here, and the cold region, the slab graveyard here. And you see the displacements of continent on top of that. And you see clearly that the continents, they go from above the upwelling zone here toward the downwelling zone. So you have a big mantle flow at the scale of the mantle in this direction. So we worked on seismic anisotropy, and I will not detail that too much. You can read the papers. You see all these bars here, colored bars, green, blue, and red, are the direction of seismic anisotropy, the S waves here. And the white lines are the kinematic directions. And the seismic anisotropy is shown in green, where you have a good fit with the kinematic direction. And you see that in that area, you have a quite good fit between seismic anisotropy and plate kinematics. Also here for India, much less so in Western Europe. At this depth, we are at 100 kilometers. If we go now at 200 kilometers, this simple thing is completely lost, and we have still a good fit between seismic anisotropy and kinematic trajectories here in India, because India goes very fast. But below Asia, this is lost here, and the flow pattern is much simpler at 200 kilometers. So 100 kilometers is the lithosphere, and 200 kilometers is the asthenosphere. Okay. And this, if you look at the 100 kilometers pattern of the seismic anisotropy, looks pretty much like what we see in the lower crust in numerical models, similar to the one I showed you for the Aegean. Okay. So the idea is that the mantle flowing underneath is controlling the system. Okay. And for this, it should be compatible with the geometry of the subducting slab all around Asia. So we looked at that, and I will not show you all the tomographic models we used, but I will summarize this on this picture here. So you have a large part of the globe here, the topography, and these are the back-arc basins. Okay. This is the Pacific slab. This is the Philippine Sea plate and slab. This is the Indian slab, it's the Indian lithosphere and the slab. You see its geometry. It's overhanging here, and it's concave up here, compression, extension. We have these arrows that we have seen before. And this is the flow at 200 kilometers. And this is the flow at 100 kilometers. Okay. And these are the main structures. So the idea is that we have a main flow that I call the Indian flow here, which is carrying the continents, and at the back of this flow we have the mantle plume, and this flow will push the or push or follow the Pacific slab retreating here, while the lithosphere here will mostly follow in this region the retreat of the Sunda Trench here. So the idea is this. Okay, you have a section here through India, Asia, Japan, Pacific Ocean. And the idea is that the flow carrying India is moving here toward the right here. And the Himalayan slab is overhanging here, detached in several pieces. And while the Japan slab here is concave up and retreating. So that's how we see the connection between the deep convection and the deformation of Eastern Asia. And merci beaucoup. I was long, I think, but.
Thank you really much, Laurent. Always weird the end of this remote. Yeah, we can have remote claps, remote clapping. Thank you really much. That was really, really nice.
Okay.
So not so easy, but do we have any questions? Feel free to just unmute yourself and ask a question.
I'll ask a question. That was just incredible. The breadth of that was incredible. And I'm afraid I'm going to ask a question on the one small thing that relates to stuff that I do. So you showed some great mafic enclaves in the granites.
Yeah.
Is there any tectonic control on how those are being emplaced and the timing of their emplacement in those granites?
So we had a detail at these enclaves, and what is quite clear is that they are more numerous in the root zone of the Pluton. That's true in Naxos, that's true in Serifos, that's true in Elba. And that's probably due to the fact that these Pluton, they have a sort of mixed origin. They are all basically granodiorites, but they have very strong crustal components. Okay, crustal melting component. They are a sort of mixture of leucogranites and more mafic magmas. And we see clearly, the best example is Serifos probably, where we see clearly that those enclaves, they are emplaced, they are still soft within the Pluton. Of course, they are stronger than the mafic magma is stronger than the acidic magma, and they are sort of dismantled in the flow in the direction of shearing of the detachment. That's very beautiful in Serifos. We have a paper on this. So the enclaves, they come as sort of dikes or necks, I don't know, and when they reach the area where the whole system is sheared, they are dismantled and they form smaller enclaves that we see today. And these enclaves, they are stretched along the general shearing direction. What's very spectacular is this transition. Could have given the seminar only on this question because it's so spectacular. These enclaves, they are what is very spectacular is the continuum we have from the emplacement of the magma, so in its still partially molten state, all the way to the myelinization in solidus conditions, and then brittle deformation. And during this thing, the enclave, they form and they deform. I don't know whether that answers your question.
No, it sounds very familiar to me from things I've seen along major slides in Grampian Highlands.
Oh yeah.
Mafic melt being injected and during deformation and then forming fabrics.
I'd like very much to see that, actually.
Any other question? Should put the chat. You can also ask questions in the chat if you feel more comfortable too.
Hey, can you hear me? It's self-breathing.
Yeah, we can hear you, Al.
Looking at Southeast Asia, I mean, I know a bit about both the Mediterranean and Southeast Asia, but Southeast Asia is where I've looked at a lot of data at the crustal scale. And I've always been fascinated since the work of Robert Hall, I think at Royal Holloway, is how Borneo rotates within this system. Because the South China Sea starts opening north-south, and then finally opens northwest-southeast. So there has been rotation of these stresses in the crust. So how does that fit with the underlying mantle and asthenospheric flow?
Difficult to say how it fits exactly, because we know much more about the history of deformation in the South China Sea than on the mantle flow itself, of course.
Yes.
I think that in general, in a broad sense, as we did in that paper, it works. I mean, it's opening toward the south or southeast, but in the detail, it's probably much more complicated than what we see. And then the interaction between the large-scale extractive faults like the Red River Fault and others, and with the back arc basin is far from understood, I think. But there is a lot of work to do, and well, this is a proposition we made a few years ago, and there is a lot of work accumulating and being published right now on the South China Sea. There's fantastic seismic profiles showing there is a lot of ductile deformation in the lower crust during drifting, and I very much to use these data to try to draw a strain, sort of a map of the direction of extension stretching in the lower crust in this region. So I'd like very much to work on these on this seismic data and to try to synthesize this and see how it fits or it doesn't with what we have proposed here.
No, Laurent, it's very good. I mean, I've been teaching the good old Tapori model for years because it explains extrusion tectonics to students very easily, but you've put a lot more detail and fidelity in how the actual system works. So thank you.
Thank you very much.
Yeah, one question I had. I really enjoyed. I mean, it's amazing to see such a view of Mediterranean geology. And I've been to look at low-angle detachments in the Al-Shahir Graben in Greece, and also I take students to the Italian Apennine. So we have these kinds of debates, and you show quite nicely that you see a lot of low-angle detachments, then followed by or cross-cut by steeper normal faults. And for a long time, there's been a great deal of debate about low-angle detachments. What circumstances are they active in? Are they different from the kind of steep normal faults that you get when you look at, or even when you look at like fault plane solutions, for example? So what are the conditions that you think that these low-angle detachments are active in, and how do they interface with the later normal faults?
Well, there are, I think, 2 points that are important in your questions. That yes, it is true that we often see these low-angle detachments cut by steep faults, and that's clearly the case in the Aegean. It's the best two best examples are Corinth and Western Turkey. It's not yet the case in the Apennines. Some of the normal faults are still active. Maybe in the Aegean it's due to the this is one interpretation. I don't know whether it's true or not, but it's due to the acceleration of extension in the recent period, due to the propagation of the North Anatolian Fault, blah blah blah, in the west, and this could make the crust more brittle if it's faster. This is one possibility. But the other solution, which I've been lingering around quite a lot, is we don't really know whether these normal faults, they ultimately are cut by steep normal fault and it's finished, or if we have all through the history of these normal faults, both low-angle normal fault and steep faults working at different times. And if you take Corinth, for instance, you have first this low-angle detachment, then you have the steep faults. But these steep faults, they root on a low-angle structure, which is diversely interpreted even by my colleagues here next door in the IPGP. But so I'm not sure it's really a two-staged process. I would like to be there in 5 million years from now to see how it goes in the Gulf of Corinth, whether we still have the same steep normal fault working or not, or the detachment that we see at depth is exhumed or not. So I'm not sure about that, because there are some. We did some numerical experiments here with Laetitia Lepouriet a few years ago, the PhD of Emmanuel Lecomte, and in these, that you take a crust and you put a discontinuity in it, which is weaker than the rest, and you pull on that, and you see that depending upon the velocity, the resistance contrast between the fault and around and so on, you have either steep fault, low angle fault, or both of them? So it's not a simple question. It's a very interesting question. It's not a simple question. But what is good now is that these low angle normal fault, almost everybody agrees that they exist. Because I have lived a period very difficult, or as soon as you mentioned low angle normal faults, you were described as a crazy joke.
Yeah, I mean, I had come through the sort of Cambridge system where the orthodoxy was that that was insane. But you go to somewhere like Elba, and you realize very rapidly that the Zuccale fault or something would have to be low angle, because even if you made it steeper, you just turn all of the thrust stack into low angle normal faults, and this does not help the problem. Exactly. But it still doesn't seem entirely resolved to me exactly what is going on.
No, of course. There are plenty of work to be done, and I'm convinced of that.
Laurent, do you want to do a PhD on this with Alex and I?
We used to joke about this with Valentin and also with Loic, another PhD student, that we should exchange our positions when he was doing his PhD.
I'll do a PhD with you. Could I ask a quick question?
Yes, please.
It's back to Al's one. Thank you for the talk. I wondered if you had a view on the origin of Bornean topography, the topography of Borneo.
Oh no, I'm afraid no. I've only worked very remotely on these areas and read the literature. Worked a little bit in the past with Claude Rangin and Manuel Cubelier on reconstructions of this region back in the 80s or early 90s. But no, I have no ideas of my own on this region.
Okay, thanks.
Nothing serious.
I can put the question in context a little bit. I suppose this debate about whether Borneo is shortening or not, or whether it's supposed by the subplate, I think is a very interesting one, which is the context for the question. Okay, thanks.
Thank you very much.
Okay, great. Thank you really much again, Laurent, to come. I told Laurent that the idea is still to invite him in person to one of our ESC departments seminar series when we will be able to do that again, hopefully in September, starting next academic year. We will see, but in the near future, we hope to see you, Laurent, in person in the department.
Thank you very much. I'm fully vaccinated, so it's fine.
And fully vaccinated, nice. Okay, great. And also, I didn't tell at the beginning why I invited Laurent. It's also because all the students before the COVID-19 pandemic were supposed to go mapping, do outdoor fieldwork mapping, their mapping project in Greece. So either in Crete, in Cyros, in Samos, and Santorini, but they were all supposed to go in Greece. So I found that it was a quite nice idea to have you with us together because you mostly spoke about the Mediterranean area and Greece. So I'm sure the students were interested to see pictures of and Cyros also. I was supposed to go on Cyros with some students. Okay, nice. So just to repeat, and if some of you arrived a bit late, the program I planned for the second part of this meeting, we will do a short break just after, but what I plan to do is to ask the year 3 students that get the best mark to the independent mapping project this year to present their work. Unfortunately, Thanos has been feeling very unwell all the night, and it's still the case today, so will not be able to present his work. So what I'll try to do, because this happens just an hour before the meeting at 11 a.m. this morning, is that to present Thanos' slides. So I'm not guarantee that it will be completely perfect. I'm definitely not an expert of the geology of Tien Shan, but just I think it will give you a good idea of what the students have done in their remote independent mapping this year, or most of the students. But what I propose, because now we have started things quite a long time, is to take, let's say, a big 10-minute breaks, and we can come back at 2:15. Yeah, so at 2:15. Yes, that's okay for everyone. We'll give time to take a cup of coffee. Okay, see you at 2:15. Excellent, Laurent. C'était chouette.
J'ai coupé mon micro. Ouais, ça allait, c'était pas trop compliqué pour eux?
Non, je pense que c'était très bien. Vraiment, ça montre comment on peut passer d'échelle en échelle, en fait, d'observations qu'on fait à l'affleurement jusqu'à aller à l'échelle de la Terre entière, quoi, ce que tu as montré à la fin. Non, c'est chouette.
Je voulais faire, ouais.
C'est chouette, c'est chouette. Bon, je vais me prendre une tasse de café, je crois.
D'accord. Ouais. Bon, je prépare une espèce de livret guide pour les Cyclades la semaine prochaine. Là.